We are from a firm called Vibrant Planet, and what we're doing is analyzing a large amount of aerial and satellite imagery combined with lots of geospatial data about what's on the ground. And there's a bunch of challenges in this, and we're going to talk about how we went about solving that problem at scale. So we are a firm that takes this information and we build up a on-the-ground picture of where are things that can burn. We map out every individual tree and how fire will move through that landscape if it happens under different weather conditions. And then what you can actually do to change fire intensity and risk to people and structures. And we kick out a set of recommendations to often consortiums of local governments saying, if you take these measures that fit within your budget, this would be sort of a cost optimal set of things that you could do to lower your community risk and make it possible to stay a place where people can live. And this has become something more of a problem, both because it's warmer, and which means that things dry out quickly, and dry wood burns really easily compared with wet wood. And also because there's a history of managing things in a way that just suppresses fire, allowing a lot of fuel to build up as plants grow more. These hotter fires are much more intense. It becomes a qualitatively different experience. If you have a low intensity fire where the flames are a few inches high, a lot of the trees survive. A lot of in the Western US, they're fire adapted or often fire dependent, and they expect that, and that would be normal. When it becomes flames 150 feet high, essentially all the trees die. It will often do things like melt pipes that are underground. It will kill off all the seeds that are in the soil so things don't regrow the same way they were before. And it's fundamentally very, very different. What we do starts off with a whole lot of aerial imagery, and from them mapping out every tree on the ground and understanding what's where, what their condition is, characterizing plant communities, and so that we can understand how things will ultimately burn if and when there's a fire. And so we built this very detailed model based on a machine learning model that collect for the aerial and satellite imagery. And then we make very specific recommendations, and this is a photo that shows 3 areas. At the top is an area where nobody did anything, and essentially everything died. In the middle is an area where people did a combination of thinning, where they removed some but not all of the trees, and a prescribed burn that burns out a lot of what's lower on the ground. And you can run those during wetter times of year when it's more manageable, and the fire would spread more slowly on its own, and so you can have some control over it. And you can see that almost everything there survived. And at the bottom, they did thinning where they removed some of the trees, but didn't do the prescribed fire. And most of what was there also died. And so it's this absolutely huge difference if you're doing well-planned management and you're funded to do it. Historically, the process for that planning was you send out a bunch of people who walk around and look at what's out there. And then they spend a year writing up a plan. And then you negotiate over, is this the right plan? Does it match our community priorities? And then they go out and draw up another plan over the next year. And it would take people often several years to converge on what are we going to do. And that's not the greatest thing in the world when you actually have a problem. What we're using Airflow for, we have all these disparate data sources where we're getting imagery and we're running fire models. We have a lot of geospatial data about where our houses and roads and power lines and critical habitat for endangered species and all sorts of things that people care about. And like everybody else, we have a DAG of DAGs, and it describes how you collect all this data, how you analyze the individual pieces, and how you put together the combined analysis, which can then give you actual recommendations for what should you go do.
So I'm gonna go back a slide for a second. So I don't know how many of you were here in the area. Do you remember when the skies turned orange? Yeah, that was the day I started looking for another job. and I found this opportunity to use my skills that I've developed so far to do something that can help that problem. I'm going to give you a quick taste of the product. So what we do is we build a Google Maps-like interface into this, and we help those people that used to take a year or so to even make a decision, to get them to make that decision faster so they can get boots on the ground and to do preventative work in, we're talking in less than a month versus a year or 2 to 10 years before a fire actually breaks out and wipes out the landscape. What you're seeing right here is our fire hazard layer. This is one of many that we have. This shows the highest area risks, the higher red, higher risk. And on this next slide, this is not meant to overwhelm. It's just a few of the different data that we collect that David mentioned earlier. We overlay all of this, and this is all interlaid in that decision support system to decide what to do in the landscape and what is the most impactful area. So you can see we have different species outlined here. We've got trail maps, we've got infrastructure, we've got buildings. All of that stuff is integrated into the product from the get-go. And how it will work is you basically circle an area of the earth that you care about managing as a land manager or as an owner for a large piece of property. And you'll start building a plan on that. And we have a series of sliders on the left so you can say what you most care about. Is it preserving your watersheds? Is it making wildfire prevention, preserving the local habitats, and then the higher areas in blue mean the more impactful areas. And then one step further is we'll generate the actual projects for you to go and actually get boots on the ground and implement changes that will prevent whatever catastrophe that you're trying to prevent. And there's more than just wildfire in here that we do. So what you see here is 3 projects, 1, 2, and 3. This is really useful because they think about different tiers of projects and different timelines. So you might implement project 1 in the first year, project 2 in the second year, and project 3 in the third year. What it also means is if you're going to only spend budget on a project, you pick project 1 because that's the most impactful area, and then project 2 and project 3. And we also have a bunch of juicy goodness in terms of stats and numbers on each of these projects. We know how much of the land it will cover, what type of treatments to do. There's a lot of different treatment types. You can throw mechanical machinery in there to remove biomass. We have cases where you have high slope. You might put a herd of goats out to remove a series of biomass, and then things like tethering, where you can hook up this like ski slope like systems to tether biomass off of mountain slopes. So that's pretty neat. We also have the financials, how much it's going to cost. We also take into account how much you can sell, what you take off the landscape for at local mills and so on. We even have distance to local mill because that does factor into the cost. So walking into our data challenge, first and foremost, we're generally working with pretty large files that we process. So we have 2 general executors. There's more. We went with the Kubernetes executor from the get-go. This enabled us to compartmentalize each of the jobs, give them a certain amount of resources, and run with them. And we weren't worried about overwhelming a single machine in that case. And how that works is every task that you spin up will go out to Kubernetes, and it will spin up its own pod. And you can size those pods the way that you need them. Our particular challenge is how we partition up the landscape. So these are called hydrologic units, HUCs. And you can kind of notice how each of these polygons are variable sized. That was a challenge, and we'll come into that later. But imagine each one of those is essentially a single task that we run through Airflow at this point. And in the early days, we looked into leveraging dynamic task mapping. Anybody that's not familiar with this, you can basically set up one task to run with multiple parameters using this .expand command here. We're passing a list of 1, 2, and 3. And how that looks in Airflow is it will generate task instances to run for each of those parameters, 1, 2, and 3. In our case, those parameters are HUCs. And we're able to scale out to, we run in the hundreds range. There is a maximum here, which is I think 1024 that you can get to. And also caveat, you want to be careful with this because that can overwhelm your scheduler when you're spinning up hundreds of things for every task. Another thing to call out is that the default memory is set at the task level for dynamic task mapping. So when you set a memory request, it's going to be, if you need 2 gigs of memory for each one of these, it's going to be the same for every task instance. And here's just a quick highlight of what a K8 pod spec would look like. We set limits and requests for CPU and memory for each of those pods that we spin up. And here's how you can interface with the Kubernetes executor. So you can use this pod override to send in that request for each task. So David mentioned that we do a DAG of DAGs. So this is something that Jason was pretty impactful in helping us get kicked off. We'll have an area of the world that we want to run. We don't do temporal daily runs. We generally do per customer demand type of runs. We'll kick off the first DAG, which will then kick off the second DAG and the third one. So we have a conductor DAG that is managing each of these. And we'll say, hey, we want to run for this area of the world. The last I checked, we got like 50 of those going, so it's pretty big. And then each one of those is doing this dynamic task mapping thing. I know we're getting a little crazy here. So we'll hit one of those little hucks will You want to make your noise? Okay. So it ooms. I'd get up in the middle of the night, and sometimes it would be I'd have to update like the tuning for the task to update the memory that we needed, or I just could restart and it would work. Either way, it was awful. And that would happen over and over and over. And we'd have to do it landscape after landscape. And many late nights led into this next piece, which I'm going to hand off to Jason.
Thank you, Cyrus. So before we get started on the solution, raise your hand if you consider yourself a lazy engineer. All right, I like it. Raise your hand and hold it up there if you have ever had to go diagnose and fix a failed task in Airflow. Keep them up there. Sweet. So that's pretty much everyone. Great. Keep it up there if you have ever had to fix a task that was not something transient and it was like less than 2 lines of code. All right. Keep up there if it was a config change. Okay. Keep it up there if it was something that was config that could have been done otherwise because all you did was increase a number. Sweet. All right. So I'm a lazy engineer. I hate doing work if I could avoid it. And every company I've ever worked at, whether it's memory, partitioning problems, I always just wonder, why do I have to wake up at 4 o'clock in the morning to just change a number? It just sucks, right? Hopefully most of you can relate with that. The problem with Vibrant Planet's problem that is slightly different from most data shops is, as Cyrus said, we don't run our jobs daily. You know, if we want to run the West Coast fire plans, we're going to run that once to completion. But in order to get there, we're adding a bunch of new features over time in how we will evaluate the landscape, some of the community pathways. And so none of our runs are really that standard. I mean, at some point, I guess they'll be more standard, but where we are today, we're constantly evolving. And these ideas of hucks being geographical shapes, which vary, as Cyrus pointed out, to being really, really tiny on the map to really, really, really big. And I think there's some really big ones up there in like Idaho, right? Yeah, giants. So this is what we kind of thought about as we were redesigning this and trying to get our team to be most effective on building as opposed to operating. So we look at try one. We throw out whatever setting, and it fails. So what do? We do the next logical conclusion. And I have a whole bunch of teammates at Netflix right now. I'll tell you, if there's a failure, just increase the memory and then start investigating. Because 9 times out of 10, by the time you figure out was an actual out of memory, it's already solved. All right, so we're going to double that. We're going to let try 2 run. All right, double resource it one more time. Try 3 runs. Boom, we're there. That's what we want, right? No one had to touch anything. It delivered. So taking a look about how this works, I will say this is a hack, but it works. Love hacks that work. So as part of this, this allows to update the pod override of a task instance for Kubernetes jobs. Specifically, setting the executor config, adding a session, take it, and then refresh the database, feel free to just steal that. Works. It's great. It is a hack. I'll let you know why it has some problems later on. And then in terms of the executive config, Cyrus kind of showed this earlier, but this is how we would basically set the memory. This job is being set to 8 gigs. For try 2 would be 16 gigs. Try 3 would be, can I do math? 32 gigs. There we go. And this is an example DAG of how we would use this. We would just basically add to our add task an on try read callback to double the memory each time and let it run. It's pretty simple. So, as a quick little proof that we're not talking bullshit, sorry for my language. So here's an example of like the retry and the failures. So as you can see, we have a total memory of 9 gigs available. There's a little bit overhead, so we only limit the process to 8.1. Filling up 2 gigs, and then out of memory. And so as part of that, we go ahead and we set the memory as part of the on-try recallback, and we set it to 18 gigs. All right, try number 2. Go up to the top. There's that beautiful 18 gigs we were looking for. Dana White would be proud right now. Here's 16.2 to the overhead. Scroll down. Another memory failure. On-try readback says 36. Let's see what that does. Oh, yes. I know it's more expensive, Max's time or the memory. Cool. But wait, I swear there's more. Okay, so one of the things we talked a little bit about earlier, when you use task instances compared to tasks, you can't set the memory per task instance as the default. And I actually don't know if there is a way to set it differently any other way. This, however, as we noted, is being set on that update task instance pod override, which gives us the ability to set this one at 6 gigs, this one at 4 gigs, that one at 64, and it can be variable. And suddenly those memory costs went down because we no longer had to set everything to 64 to make them all succeed. So for us, from a business perspective, this is a large cost saving for us. Forget people saving. This is like direct compute cost at that point. All right. So setting initials per TI. Try 1. I want you to imagine I lied to you, because I did. Try 1 is not what it looked like before. Try 1, what happens when we run it? It auto fails now. Why does that happen? Well, as part of that hack I mentioned before, Airflow loads it the memory settings directly from the config. And so you would have to put a static number there, and you would still have that same problem around all the tasks being set the same and not being able to come up with any fun stuff on your initial allocation. Because you would have to either write a code generator to do it on check-in, which means you couldn't use like any additional features that you want to add into the estimate. So what we decided to do was we immediately fail every single task as our first iteration. We then log a bunch of stats collection data from every Airflow task that we run. So we actually know what tasks are running per task instance. And we use those to figure out what it should look like. So now we get back to the rest of the presentation. Try 2, aka try 1. Double resources. Try 3, aka try 2. Go one more time, double resources. Try 4. Boom, success. All right, I'm gonna kick it over to David. He built out a lot of this initial memory source work, which is really cool.
Yeah. When we run it that first time, we are doing that automatic initial failure initially, just to give us the ability to do an estimate of what we actually need. And that's all it does. And so we have some very simple heuristics for what we're going to do. And so if we've run the same task on the same data before, we know what its needs are because we were logging it. And so we can give it that amount of resources and give it a safety margin in case somebody made a change or something that needs a little bit more. If we've run the same computation before, but on other data, we have a statistical description of our data that characterizes it, in our case, by area. And you can just run a linear regression. And in most cases, that gives you something useful in terms of a good estimate of what the resource needs are going to be. And so you can use that plus a safety margin. The unit of work is a hydrologic unit. And the actual area we're using is a bounding box area rather than the area of the unit itself. But that's going to depend on your particular application's data. You're going to want to understand your own data and what about it causes you to need memory to do analysis. We have a couple more slides. We have one last case there, which is that if we don't know anything because somebody's bringing up a new DAG or a new task, we just make a guess. And because we'll double the amount of memory afterwards, the fact that the guess is not perfect really doesn't matter. It just matters that we're making some vaguely reasonable guess. We actually wrapped the whole thing in a custom decorator. And what that means is that the people writing DAGs don't have to understand any of this. All they have to know is you use our decorator, which is at task.vp for Vibrant Planet, instead of at task, and you get all this functionality, and it just happens. And so it's very easy to pass that out to a larger team. And it gives us four important things. One is it has a stats logging that logs actual usage of resources by the individual task. It does that initial memory recommendation. It does the memory ramp on retry, and it does out-of-memory detection. And that it's a wrapper ends up being important because you can monitor child processes.